Hi, guys. Yep. There we go. Good. How's everybody doing today? Good. So just some administrative stuff before we get started. We are going to start the multivariable book today. Today is, you guys can get a copy of the multivariable book. That is something you'll need when you do Calculus 3, the multivariable book. I posted homework for chapter 1.2. I know our syllabus says 1.1. I'm going to breeze through 1.1 really quickly with some definitions. Don't worry about doing the homework for 1.1. I know some of my colleagues actually skipped that whole chapter altogether. So don't skip the 1.1 stuff. I'm just going to try to go through it fairly quickly so that you guys have, excuse me, so that you guys, we have like a common vocabulary when we talk about certain things. 1.2 is where like the meat of things starts to pick up. Okay. So I posted the homework for 1.2, but the homework for 1.2 isn't due until next Thursday. So not this Thursday, but next Thursday. So you have plenty of time to take a look at that. I recommend waiting till after your exam to look at the 1.2 homeworks so that you don't overwhelm yourself with stuff that's not going to be on the exam that's this week. So our exam is this Thursday. Don't forget, it's going to be on chapter 3, chapter 5, and chapter 4.5 and 4.6. Okay, the 4, 5, and 4, 6 stuff that we went back over, and we did the power series. We found the radius and the interval of convergence, and we found we were able to see whether that interval actually contains the points or not. Okay. I was looking at some of your homeworks for that and some of the quizzes for that. You guys must show me the checks, the endpoint checks, in order to receive credit on these things. Okay. Also, you guys probably noticed too that I posted a bunch of homework, so, like I graded your homeworks for completion, and I graded a bunch of the quizzes. Okay, I actually was hoping that we could go over some of the quizzes, but we probably won't have time today. If you guys have questions on them, we can talk about them on Wednesday, which is our review period. One of the things that I noticed on the quizzes were that, one, when you guys are going through things like series, like you're going to check your series stuff, make sure that you're showing me all of the work, right? You can't just say this thing diverges or converges. You have to tell me like what test you're using. You have to say what was the criteria for convergence or divergence, and then you have to say what was your final conclusion. Therefore, it diverges by the p-series test or whatever. Okay, I have to see all of that. Chapter 3.5, the volume of revolution. The quiz just did around a horizontal axis. Okay, I need to see how you got the points of intersection. Okay, between these two graphs, you have to show that you set the two functions, equal to each other. Right, and that's how you solve for x to get the points of intersection. Okay, I have to see that. Also, things like finding the let's see, what is it? Finding the total distance traveled. Make sure that you're testing, right? If it's a straight line and we just have some kind of a function, right? Make sure you're testing to see where does that velocity go negative, because you have to multiply that portion of the equation by -1 to make it positive. If you're dealing with a vector, right, your total distance traveled is going to be based on the magnitude of your velocity. So if you're given the position, make sure that you make sure you differentiate first, right? You get the derivative, and then you take the magnitude for that. Okay. I'm going to post solutions for those quizzes so that you guys can see, how those things work through. You can have those things to study for. So Wednesday is going to be a review period. I posted over the weekend old exams for exam number 2. I think they all have solutions on there. Please come prepared on Wednesday to ask questions. You can ask questions on homeworks, on lecture examples, on quizzes, on the old exams, whatever you'd like. That hour or 65 minutes is for you to ask questions. Okay. Let's see, have I covered all of the administrative stuff yet? I think that's about it. Remember, the midterm is not cumulative. It's just the stuff from the last midterm exam, okay? But our final exam will be cumulative, and the final exam will include stuff like the multivariable stuff, which we're gonna start today, okay? So with that said, I've got lecture examples for 1.2. We don't have lecture examples for chapter 1.1. 1.1, we're just going to go through fairly quickly to give ourselves a common vocabulary on some stuff. And then we'll jump right into 1.2, which has a lot more details about vectors and things that you'll need to work it through. Okay. Phew, a lot of things to think about. 1.1. Oh, I also forgot to mention too, this Thursday we have homework that's due. And the homework that's due on Thursday, I think, is for chapter 3.9. So keep that in mind, okay, for things that you need to make sure that you pass in. All right, chapter 1.1. So this is Euclidean space. Oops, Euclidean space. Okay, so I think my pens are starting to run out of ink a little bit. So I'm going to go through some of the stuff you may have had in other classes. So, you know, hopefully maybe it isn't completely unfamiliar to you. But let's talk about dimensions and dimensional space. So if I talk about one-dimensional space, okay, I'm talking about like a number line. And I want to say I've got all real numbers in one-dimensional space. So I've got this all real number symbol with, this is not like going to be squared or cubed or whatever, but it tells me how many dimensions I'm dealing in. So I've got all real numbers in one-dimensional space. I've got a number line. We typically say X. I've got an origin. I've got a couple numbers A to B. If I want to be able to calculate out the distance from A to B, I'm going to take the absolute value. Doesn't matter if I go A minus B or B minus A, because I'm taking the absolute value, but I can also think about it as B minus A squared, square rooted. Same idea. This is like the mathematical concept of what we're trying to do here. Okay. That's for one-dimensional space. If I'm in two-dimensional space, right, we say we've got all real numbers in 2 dimensions. It's not R squared, it's 2 dimensions. Right, we're dealing with X, Y. Now let's say, for example, I've got a couple points, X2, Y2, X1, Y1, and I want to calculate out the distance d between them, right? We would think about our Pythagorean theorem, right? So I've got the difference in the x's, the difference in the y's. Pythagorean theorem says a squared plus b squared equals c squared. So we can use that for our distance formula, right? I can say x2 minus x1 squared plus y2 minus y1 squared, sum it up, square root it. Okay. It doesn't matter if I do x1 minus x2 as long as I keep the subscripts the same for both x and y. I'm looking for the difference between them. Okay, this is my distance formula, so the distance between x and y as points. Okay, now if we do 3 dimensions, right, all real numbers in 3 dimensions. Okay, we would say, I'm going to draw this out like this. You can imagine my negative z, my negative x, and my negative y going off into the page. Say, for example, sometimes we draw it from here and we draw it coming out of the page, right? Like out here, it's harder to visualize. Now, if I've got points here, I've got, in 2 dimensions, I've got an x and a y, which is an ordered pair. If I'm in 3 dimensions, I have an x and a y and a z. It's an ordered triplet. Okay, so what happens is I'm going to go over x, over y, up z, like I'm here, and I'm going to go come off the page for my z axis. It's hard to do that on the page, so I always end up kind of having to squash it, like z2, I've got x, y, z, and then let's say I've got another point x1, y1, z1, and I want to find the distance between them. It's the same thing. It's harder to draw and to formulate what that means in terms of 3 dimensions, but the math is the same. It just scales up. Squared plus y2 minus y1 squared plus now our z, z2 minus z1 squared. Sum it up, square root it. Okay, that gives us the distance between these 2 points in space. Okay, 1, 2, 3. We typically focus on these because we can visualize them fairly well, but I can extend this math out into n dimensions. and say all real numbers up into n. And so then my, it would be like a, I would say I've got x1, x2, x3, and so on up to xn. We don't, when we get beyond x, y, z, we start just kind of calling it x1, x2, x3, x4. They just become components in what we call an n tuple, right? Where n is our dimension. Okay, but to find the distance between two of the same dimensional points, right? I would just do this out to how many dimensions do I have? Out to n dimensions. Okay. Right, like I said, we're just doing vocab. There's a lot of vocab in 1.1. It's going to go pretty quickly. Whoops. And there's other stuff in here. If you guys have the book, I encourage you to take a look and read it. There's things that I'm skipping. You're going to be getting more of this stuff next semester when you take Calculus 3. But in terms of what we're actually trying to do with multivariable, there are things in Chapter 1.1 that we're not going to worry about. There's some symbols, like you've got this thing, it looks like an elongated C. This just means subset, right? So I can say the subset of all real numbers, you know, that are odd. Say, for example, I would define it, this is the subset, just in terms of like how we want to relate things. Let me see what else I want to cover. I think that's, all right, I think we're good. There's some other vocab too in terms of like union and intersection, but I'm not going to worry about those. We'll get those in other areas. Okay, so 1.1, very quick, right? Don't worry about, I know our syllabus talks about homework problems for 1.1. I'm not posting them. I'm going to start off with 1.2. We're going to really get into the meat of it in chapter 1.2. You've got homework for 1.2. I've posted it already, or I just posted it, and then you'll be able to see that. But that won't be due until like in 10 days, like till next Thursday, April 8th. Okay, so don't sweat that one right now. So that's 1.1 in terms of what we wanted to worry about. So 1.2, we're going to get actually into the meat of things. So chapter 1.2 is in our dimension, n-dimensional space, all real numbers, n-dimensional space. We're going to talk about vectors. And really, like, what's going to happen the rest of chapter 1 is we're going to go into a lot of details about vectors. So we're starting to introduce them in chapter 1.2, some basic properties about them, how we can tell certain things, how do we define certain stuff, how do we do certain things. And then in the rest of it, chapter 1.3, 1.4, 1.5, we're actually going to be doing, using vectors. We're going to multiply them. We're going to use them to describe all sorts of stuff in, say, 2 or 3 dimensional space. Okay, so but right now let's just kind of talk about some basic properties. So when we have a vector, and we kind of covered some of this stuff in chapter 3 a little bit. So a vector has a magnitude, and let's do magnitude and direction. So magnitude basically tells us the length of the vector, and the direction is actually a mathematical property, but we tend to think of it as which direction is it pointing in, but this is actually a mathematical property that we're going to talk about in detail today too. As opposed to a scalar, which is just a number, a plain number. So it has just magnitude, no direction. Right, so this is like, you know, 2, 3, pi, 7.5 minus 11, you get the idea, right? So this is a vector. We're going to write our vector. It's going to have like an arrow over the top, because some books will do it bold. I can't do bold on a piece of paper, it's harder. So I put like an arrow, or I do like a half arrow like this because it's easier to draw it. Okay, so when we talk about a vector versus a point, we're going to talk about what that looks like. Okay, so now there's a thing called a displacement vector. So displacement vector basically is a vector that represents the displacement or the distance between 2 points. Oops, displacement or distance. And I really want to use the term displacement because it's a vector. And we think we just defined in chapter 1 distance as being like a scalar. Okay, so we're going to be talking about this really more as a displacement. So you can think I've got, let's say, 0.1, and I'll call that A and B. I've got components A and B. 0.2 is going to have components C and D, say for example, and then my displacement vector, I'll call V, is going to be, I'm going to call that, I'm going to start at 0.1 and I'm going to go to 0.2. So this tells me I'm going from 0.1 to 0.2. Okay, I've got this arrow over the top here. Okay, so 0.1 is our initial point. 0.2 is our terminal point, where we're ending. To calculate, to come up with a value for our displacement vector, we're going to go terminal minus initial. So if our displacement vector is P1, P2, which is equal to V, then we're going to say our terminal, which is P2, minus our initial, which is P1. So say, for example, if our P2 is CD minus AB. So our displacement vector is going to have components C minus A and D minus B. We'll do actually examples like this, and this will be a vector that represents, right, this displacement from P1 to P2. That's our displacement vector. Okay. Now, when I talk about the magnitude of a vector, right, I'm going to write it out like this. It looks like absolute value, but it's really telling us we're going to take the magnitude of this vector. So if V has components V1, V2, V3, and so on, all the way up to V sub n, right? These is like, I've got, you know, maybe 11 different components in my vector V. It's an 11-dimensional vector. To calculate its magnitude, I'm going to take each component, square it, sum it, and then square root it. The magnitude is always positive. If you get something that's negative inside your radical, or you're thinking, oh, the magnitude is going to be an imaginary number, it means probably your calculator misled you. So if one of your components is -4, for example, and you go to square -4, like if I type in my calculator -4 squared, it does an order of operations, does the exponent first, so I get 16, and then it multiplies by a -1. So I get -16, which is not what I wanted. So I have to do parentheses. -4 in parentheses squared gives me +16. So make sure when you're doing this, sometimes I'll just write parentheses around everything just to make sure I'm not, you know, confusing myself about negatives, especially when I'm going fast and I'm trying to do stuff like on a quiz or a test. Okay, so I'm looking at my lecture examples for chapter 1.2. Lecture example number 1 says, we've got this vector here. What's our magnitude of F? So I'm going to take my F, take the magnitude. I'm going to take each component, I'm going to square it. So you notice the -2, I'm going to square that in parentheses, add it all up, and then take the square root. So this is 9 plus 4 plus 16, right? This is going to be equal to radical 29. And this is our magnitude, okay? You can leave things in simple radical form. You don't have to like give me like a decimal or anything like that. So just leave it like this. Okay. So this one here is kind of like what we did in chapter 3. Okay, so we've got velocity and the speed. So the speed is the magnitude of our velocity. Okay, so I'm going to take this here. It's already in velocity. I don't have to do anything. I have to take the derivative or whatever. It's already in velocity form. So my speed, I'm going to take 2 cosine of t squared plus 2 sine of t squared plus radical 5 squared. Sum it up, square root it. This becomes 4 cosine squared of t, or sine squared of t, plus 5. I'm going to factor out 4 just here in this little mini thing. Cosine squared plus sine squared plus 5. Don't forget your radicals. This is equal to 1 by our Pythagorean identity. So this just becomes 4 plus 5, which is radical 9, which is equal to 3. And I think, were we in meters per second? Okay. Because we've kind of done some of this stuff in chapter 3. It's going to be a little bit of a repeat because chapter 3 we started talking about vectors, right? That was a vector function. Okay. All right, so let's keep going about stuff that we can do. All right, there's something I want to throw out as a concept, something called the zero vector. Zero vector, we often call it zero with the bar over it, or it'll be like a zero that's all bold in some books. And what this means is I've got a vector, you know, an n component vector, all of them are 0. This is really a point vector. This is like saying our origin is a vector. And this in linear algebra allows us to do certain things, like I need to combine stuff with the origin, but it has to be vector plus vector. So that's why we can label our origin as the point vector. It's called our zero vector. It basically has no direction and all direction. You'll see why in a minute, because direction requires basically dividing by the magnitude. And this thing has a magnitude equal to 0. Okay, it's really a construct. It allows us to do stuff in linear algebra. So if you take linear algebra, which I think as engineers, you'll take differential equations in linear algebra, you'll be using the zero vector to do stuff. I'm just pointing it out as a, but it's really like a concept. Vector addition, let's talk about that. There's a geometry to vector addition in addition to like the algebra behind what we need to do. So let's say I've got the vector A, which has components A1, A2, A3, all the way up to AN. So this is all real numbers in n-dimensional space, whatever n is, you know, could be any dimension. I've got the vector B, which has components B1, B2, B3, all the way up to B sub n. So that's also in n-dimensional space. If I want to add the two vectors together, they must have the same dimension. Right, like if you're adding things and then you realize, I've got some bits left over, what do I do with those? You can't add those, okay? They have to have the same dimension. When I do this, I'm gonna add corresponding components. Right, so A plus B is equal to A1 plus B1 in the first position, A2 plus B2 in the second position, A3 plus B3 in the third position, and so on and so forth, AN plus B sub n. Okay, this is A plus B. Corresponding components get added together. Okay, that's our vector addition. Subtraction works the same way, except I'm going to add a negative number. But let's talk about the geometry on this. There's a thing called the parallelogram rule, which talks about if I've got the initial point of A lined up with the initial point of B, or both of our vectors here. Okay, these form a parallelogram because you can imagine I've got a scalar version, a parallel version. This is like another version of A. That's an A right there. And I've got another version of B right here that lines up with it. The diagonal of this parallelogram is the sum of these two. Okay, that's our parallelogram rule. When you go to add A and B, if you have vector A on, like if you can plot it on a graph, you have vector B plotted on a graph, and you get their corresponding components and you plot that, you'll see that forms the diagonal of a parallelogram. Subtraction is the same thing. I would go A plus a minus B. We're going to talk about scalar multiplication in a minute. This is an arrow. Scalar multiplication in a minute, but what this minus B says is it's the same thing. Let me draw this out again. So here's my A, here's my B. Minus B, what I've done is I've multiplied B by -1. It's equal to B in magnitude, but it's pointing in the opposite direction. Okay. Now you can imagine I've got a parallelogram this way, and then there's some a plus a minus b goes here. So this is a minus b. So here's a, here's b, here's a minus b, but it comes from a plus minus b. Here's our parallelogram. Okay, so our parallelogram rule for addition and subtraction. Subtraction works the same way as addition, only we're multiplying by a -1. All right, let's try example 3 on our lecture examples. Example 3 says we've got two forces, F1 and F2. What's the magnitude of the net force? Net forces are some of our two forces. So my force net is going to be F1 plus F2. Okay, so I'm going to go F1, 2, 3, minus 5 plus, minus 3, 1, minus 2. So my force net is 2 plus a minus 3, 3 plus 1, minus 5 plus a minus 2. Is that a minus 5 or positive 5? Oh, I got confused. I thought that's really positive 5. Looks like my own box got me confused. That's positive 5 plus a minus 2. Sorry about that. Couldn't read my own writing. Okay, so this becomes 2 minus 3 is minus 1. 3 plus 1 is 4. 5 minus 3, 5 minus 2 is equal to 3. So this is our net force here. And now I want to be able to find the magnitude of the net force. I'm going to take my components and I'm going to square them. I'm going to sum up the squares and I'm going to take the square root. So this is 1 plus 16 plus 9, which is equal to 26 inside the radical. Okay, and this is Newton's also. Okay, you may have seen stuff like this in your physics classes. Okay, so we're dealing with the magnitudes here. You guys all set with this here? All right, so what I'm going to do is I'm going to talk about scalar multiplication. This is a scalar times a vector, so we call it scalar multiplication. So we'll say scalar times a vector. Subsequent chapters 1.3 and 1.5, I think, deal with vector multiplication. That's our dot product and cross product. We're going to be talking about that in depth because they're pretty important processes. But right now, just for today, we're talking about scalar multiplication. So scalar, remember, is just a number, a plain number, and vector has got multiple components to it, right? So when I want to do a scalar multiplication, I have to take that scalar and I have to distribute it and multiply it by all of those individual components of my vector. So let's say I've got a vector v, v1, v2, v3, and this is our vector. And I've got r is our scalar, and it could be equal to 2 or minus 3 or whatever, it could be some number. And if I do scalar multiplication of r times v, this is like saying r times v1, r times v2, r times v3. Okay, I have to distribute that r into all my components. All right, so what can happen? Let's draw out a picture. Say I've got my v right here, okay? And I'm going to multiply by 2. So I've got a vector that's 2 times v. So this is 2v. It's a vector that's twice as long as my original vector, right? If I want to multiply by a negative number, so here's my v. If I'm going to multiply by a negative number, here's minus v. It's the same thing as v, only it's pointing in the opposite direction. Right? You can imagine if I did minus 2v, I'd have one that was twice as long as my original, but now pointing in the opposite direction. So if the scalar is negative, it reverses the direction of original vector. If it's negative and it has like a number, so if it's -3, it's going to reverse direction and it's going to extend its length. Okay. Now, if I want to calculate the magnitude of a scalar that's being multiplied by a vector, right, I can say I've got this magnitude of r times v, right? R is my scalar. That's going to be the absolute value of r, right, because I want it to be positive, times the magnitude of v. Okay, we're going to do an example where you'll see if I don't factor out the r and then just multiply it, if I keep it inside, like if I distribute it, okay, this is equal to rv1 squared plus rv2 squared, and so on and so forth, summed up and squared. Okay, I can factor out that r, right? I can factor out an r squared, and I can just be multiplying it by r, my magnitude. Okay. It's a shortcut. You can always multiply it through and take the magnitude, which we'll do. So example 4, we've got an object with a mass 10 kilograms, acceleration is a vector, radical 6 minus 3, 1 meters per second squared. What's the net force? What's the magnitude of the net force? So remember, our force, mass times acceleration. So this is a scalar. Mass is a scalar. Acceleration is a vector. So we're going to say 10 times radical 6 minus 3, 1. Okay, so my net force is going to equal to 10 radical 6 minus 30 and 10. Okay. Now, this is in newtons. Okay, now if I want to take the magnitude of my net force, let's say net, right? The magnitude, we're going to do it like the long way, and you can see how if we factored out a 10, if I just multiplied it by 10, what it would look like. So the long way is 10 radical 6 squared plus a minus 30 squared plus 10 squared. Sum it all up, square root it. So this becomes 100 times 6. Watch, I have to do 10 squared times radical 6 squared plus minus 30 squared becomes not positive. Okay, this is equal to 1600, which is equal to 40 newtons. You can imagine, right, if I factored out my 10, so if I said the absolute value of 10, times the magnitude of the force. So I go 10 times radical 6 squared plus minus 3 squared plus 1 squared. So this is 10 times, this is going to be 6 plus 9 plus 1. 10 times radical 16, so 10 times 4 is equal to 40. It's the same thing, okay? So either way, however you want to think about it, this is always correct, this is also correct. Okay. I'll let you guys finish writing that and we'll go back to notes. Are you guys good with that? Okay. All right. So let's think about our what's called a unit vector. So we talk about our vectors. Unit vectors, and we'll go this the process of normalizing. Normalizing is important in linear algebra because it allows you to kind of all compare apples to apples instead of all these different vectors. So if I have a vector and it has a magnitude, right? A magnitude would be equal to some number, right? Now, if I take my vector and I divide it by its magnitude, this will give me a unit vector. Sometimes we call this v hat, we call it like that. You can just call it a unit vector, it's fine. This has magnitude equal to 1 unit. That's why we call it, it's our 1 unit vector, has magnitude equal to 1, okay? I divide it, I normalize it by its own magnitude, okay? So this also is the mathematical definition for calculating the direction of a vector. So vectors have magnitude, they have direction. We usually think of direction as the direction that it's pointing, but it's also true that the vector divided by its magnitude gives us the mathematical quantity for its direction. Okay. All right. I think let's do quick. We'll do an example really quick before we move on to parallel vectors. So okay, good. So this one here, example 5, basically says we've got this. We want to calculate what's the displacement vector from point P to point Q. So point P is our initial point, and Q is our terminal point. And then we want to be able to find the magnitude and direction of the vector that results from that. So I'll call this V equals, I'm going to go from P to Q, right? So remember, the displacement vector is our terminal minus our initial point. So my terminal point is Q, so this is going to be Q minus P. So this is minus 3, 0, 4, minus 1, 2, 3. So this is going to equal to minus 3 minus 1 minus 4, 0 minus 2, 4 minus 3, positive 1. So this is our displacement vector between points P and Q. To find the magnitude of V, right, I'm going to take each component, I'm going to square it, but watch how I'm putting things in parentheses so that I keep my calculator honest if I'm doing this on a calculator, so I don't get a negative magnitude, which would be incorrect. Minus 4 squared, 16, 4, 1. By the way, I saw on the quiz you guys made some simple algebra mistakes. 4 squared is not 8. Be very careful. 4 squared is 16. I know you're going really fast. You're probably stressed out. Just make sure, take a breath. Make sure that you're getting your algebra right. So this is going to equal to radical 21. And this is in meters. This is our magnitude. Okay. Our direction is our vector divided by its magnitude. So my vector, minus 4, minus 2, 1, divided by radical 21. I can leave it like this, or I can distribute it. So minus 4 over radical 21, minus 2 over radical 21, 1 over radical 21. Don't worry about rationalizing these radicals, just leave it in the denominator, okay? And this is unitless, okay? Can you guys all have that okay? All right. Let's talk about what it means to be, for two vectors to be parallel. I know there's a lot of topics in this chapter section. There's a lot of details that we have to think about. And you know, give yourself a chance. There's a lot of homework problems for this too. They're pretty straightforward, but there's a lot of them. So give yourself time, but don't even look at the homework until like this weekend. Like study for the exam and then look at the homework later. Okay. So we talk about parallel vectors. I'll say V parallel to U, for example. I'll put a question mark. So when two vectors are parallel to each other, what does that mean? It means that they are scalar multiples of each other. Okay, so if this is true, then that means V is equal to R times U, where R is a scalar. Okay, which means that every component of V is equal to the scalar multiple of that component, corresponding component in U. So I'm going to say V1, V2, V3, for example, is equal to R U1 R, U2, R, U3. Okay, where R is our scalar, it has to be the same R. Same R, same scalar on each component. If one of them is slightly different, even if it's negative R, then they're not scalar multiples. Okay, so it's part of our check. This is our check to see if two vectors are parallel to each other. It's our most basic check. We can use, we'll learn later, we can use the cross product to help us figure out if things are parallel to each other, but that's kind of overkill. I can just check to see if they're scalar multiples of one another. So let's take a look. Example 6, we're given 4 vectors. We want to see, are any of these vectors parallel to each other? So we're going to go through combinations, A to B, A to C, A to D, B to C, B to D, and then C to D. Okay, so we're going to go through, you know, several of these, right? And then we're going to see what's true or not. Okay, so the first one that we're going to do, I'm going to check A parallel to B, and I'll put a question mark. Okay, so that means what I'm going to do is I'm going to specify the components of A, 2, -3, 0, 4. Okay, and then that has to be equal to R times the components of B. So it's going to be R times -3. That's going to be R times 4. It's going to be equal to R times 0. So it's good that we have 0 in the same place. Okay, because if this was 0 equals R times 1, then we would know that that wasn't going to be true. And this was R times, where am I? -6. So now I need to solve for R and then check to see if they're the same or not. Okay, so I'm going to go like this. R equals 2 divided by -3. R equals -3 divided by 4. Okay, so already I have a mismatch. Okay, if I get an R that's a mismatch, it means that they're not scalar multiples. I don't even have to check the rest of them. Okay, so A is not parallel to B. Okay, because I have an R mismatch. It doesn't matter if the rest of them match. If one of them doesn't match, then they're not parallel. Okay. So let's try A to C. A parallel to C. I'll put a question mark. Guess we're going to do the same process that we did, right? So I'm going to list the components of A. So 2 -3, 0, 4 equals R, my scalar, times C. So this is going to be equal to R times -1.5. R times 2, R times 0, R times -3. And I'm going to solve for R. So R is equal to 2 divided by -1.5. R is equal to -3 divided by 2. So it looks like I've got a problem again, right? And this is equal to R equals 4 divided by -3. So there's a mismatch. Okay. R's don't equal, so then we can say A is not parallel to C. I'll do one that actually is so you can see. So we'll do B parallel to C, and I'll put a question mark. I'll tell you ahead of time. This one is, and you'll see why. So let's do the same process. So I'm going to list the components for B, -3, 4, 0, -6. And it doesn't matter what order you go in because you're just checking for the same scalar multiple. R times C. So it's going to be equal to R times -1.5. R times 2. R times 0. R times a -3. So now I'm going to solve for R. R equals -3 divided by -1.5. R equals 4 divided by 2. This is 0. R equals -6 divided by -3. So it looks like our R is equal to 2. Okay, on all, same R for all components. So therefore I can conclude that B is parallel to C. The other ones are not. Okay, so B is not parallel to D, and then C is not parallel to D. Okay, you can go ahead and prove those to yourself. I'm going to skip for time purposes. Okay, so you have to check each component to make sure. Okay. Right. All right. So let's go and we'll talk about example 7. So find a unique vector v, which has the same direction as w, but which has a magnitude equal to 7. So let's remember our direction is the same thing as calculating out our unit vector, right? So I'm going to calculate out my w divided by its magnitude. So this is 1, 3, 2 components. 1 squared plus 3 squared plus 2 squared. I get loose with the parentheses because they're all positive. This is 1 plus 9 plus 4. So this is 1, 3, 2 divided by radical 14. Okay, so this is our unit vector of w. Okay, this has a magnitude equal to 1. It's a unit vector, so its magnitude is equal to 1. If I multiply it by 7, it'll have a magnitude equal to 7. Okay. By 7 to get magnitude equal to 7, because we want a unique vector which has the same direction but has a magnitude equal to 7. So now I can say my v is equal to 7 times 1, 3, 2 divided by radical 14. Or I can write it like 7 over radical 14 times 1, 3, 2. And I can distribute this into here, or I can leave it. And that's equal to v. Okay, so you're kind of working your way through the thought process on it. Okay. This last one here is what we call a linear combination. Of vectors. And you have to remember your order of operations. I can add and subtract my vectors as though it was like an equation. So 3u plus 7v. I'm going to say 3 times u, 1 minus 1, 2, plus 7 times b. Okay, before I can add them, I have to multiply through my scalar multiples. So this is going to become 3 minus 3, 6, plus 28, 21, minus 35. And now I can add component to component. So this becomes 3 plus 28. Okay, this becomes minus 3 plus 21. This becomes 6 minus 35. Okay, so this is 31. This is 18 minus 29. That's our linear combination of our vectors. Okay. All right. One last bit, there's something I want to mention. I'll let you guys finish writing that, and then we'll talk about a last concept about vectors. So there's a concept called our standard unit basis vector. And what these things represent are, I've gone out 1 unit in my x direction. Which I would write as 1 unit in the x and 0 in the y. Or if I was in 3-dimensional space, I would go 1 unit in the X, 0 in the Y, and 0 in the Z. I'm going to go 1 unit in the Y direction only. So I've gone 0 units in the X and 1 unit in the Y. Or if I'm in 3-dimensional space, 0 units in the X, 1 unit in the Y, and 0 unit in the Z. If I go 1 unit in the Z direction, that's only in 3-dimensional space. Okay. These things are given letters. I as our unit basis vector for the X, J as our unit basis vector for Y, and K as our unit basis vector for Z. How this looks in 2 dimensions, right? I've gone, so this is, I've gone 1 unit in the X direction. I'm trying to really emphasize it here. I've gone 1 unit in the Y direction. Okay. Same thing in 3 dimensions. Okay. So I'm going to go 1 unit in the X direction, 1 unit in the Y direction, and 1 unit in the Z direction. These things are important because they allow us to do linear combinations of a vector. So I can say V is equal to, let's call it 2 minus 6, 3. If I want to break this down or represent V using my unit basis vectors, I would say I'm going to go 2 times I plus a minus 6 times J plus 3 times K. Because what this looks like is 2 times 1, 0, 0, plus minus 6 times 0, 1, 0, plus 3 times 0, 0, 1, which is the same thing as 2, 0, 0, plus 0, minus 6, 0, plus 0, 0, 3. Now, if I were to sum up this vector here, I would get 2 plus 0, 0, 0 plus a minus 6 plus 0, 0 plus 0 plus 3, which is what I had to start with. So this is just another way. This is equivalent to writing it like this. Okay, these are ways of writing out vectors. Okay, unit basis vectors are important because they also allow us to normalize things, and I can use various standards as a basis vector. This is that comes into play more in linear algebra. Okay, but I can represent a vector as a linear combination of my unit basis vectors, I, J, and K. Okay, so this is just a concept that I'm throwing out there because we want to be able to use it when we talk about other stuff. Let me think. And I think that's about it. I think we're good for chapter 1.2. All right, so that's chapter 1.2, okay, and chapter 1.1 in terms of the stuff that we're going to cover. Like I said, don't worry about starting the homework for 1.2 until after the midterm. Okay, guys? Phew, a lot of stuff to think about. Does anybody have questions on homework stuff or quizzes that you wanted to ask about? We've got about 10 minutes. I can answer questions on stuff. If you want to ask anything, you can put it in the chat if you want. I can do homework, so I can do. I posted quiz answers, but I haven't posted quiz solutions yet. If anybody has any questions about it, I did notice a number of problems on the quizzes with the points of intersection. We were just going around a horizontal axis. Okay, so you have to make sure you've got your outer radius and your inner radius calculated correctly. And the points of intersection, you must show the algebra on those. Okay. Can we go over the quiz solutions? Yes, which one? We had 3 quizzes that I just finished grading. Which chapter? Which quiz do you want to talk about? Most recent, 3.5, perfect. All right, so these are my quiz solutions. So question 1, this is the chapter 3.5 disk washer method. And if you guys don't want to hear this, you're good on all this stuff, you're free to leave. And we're just going to go answer questions here. All right, so question 1, we've got the region between the graphs x² + 2 and 4 - x². right? So I like to graph these out, but that doesn't count as like, you can't just look at the graph and say, what are our points of intersection? So we didn't give you a range of values to integrate from. So if you don't have that, you have to find the points of intersection between these two. So I have to set the two functions equal to each other. And then I solve for x. I get x equals plus or minus 1. That gives me my bounds of integration, right? We were told to go around the x-axis. Now I have to think about, let's write it like this. I've got my outer, and I've got my radius inner. So I have to figure out which one's the outer and which one's the inner, right? So I have to take a look. 0 is a good spot. So I go f of 0 is equal to positive 2, and g of 0 is equal to positive 4. So g is our outer radius, and then f is our inner radius, okay? So I'm going to say I'm doing the disk method, so I'm going to do slices, areas, cross sections of areas. So it's pi r squared. So it's pi times my outer radius squared, integrated from -1 to 1, minus my inner radius, pi r squared. Okay, and I just put it together. This was just a setup problem. You didn't have to do actual integration. A lot of times on the exams, we just ask you to set up the integral because integrating is going to be trivial. Question 2, we didn't give you a bounds for integrating, so you have to find the points of intersection, which when you go through the algebra, you have to show the algebra. This is what we'll be looking for, say, on the final exam, right? I have to do, I found 0 to 16. This goes around the x-axis, okay? So I have to look for my upper function and my lower function, right? So I can choose some value, right? So if I go, so at x equals 1, so if I say y equals radical 1, that's 1. Y equals 1/4 times 1, that's 1/4. So my radical x is my upper function, which makes that my outer radius. Okay, our outer, and this is our inner. You can ignore this line here, that was a mistake. Okay, so now I've got my pi r squared from 0 to 16. So pi r outer squared minus pi r inner squared. And that was it. Okay. Question 3, we're going around a horizontal axis, but it wasn't the x-axis, it was y equals 7. So I've got these two functions. Again, we don't have a bounds of integration, so I have to set the two functions equal. I get a quadratic. I use the quadratic formula. I found x is equal to -2 and +1 as my points of intersection. So I've got this here that's going to go around the axis y equals 7. So I'm going to go, my outer radius is from 7 to here, which I have to plug in values. I can plug in 0 and find out which one's greater, right? So if I do x equals 0, I'm going to get y equals 3, x equals 1, I'm going to get y equals 1. So this one is our outer function, right? And then this one is our inner function, okay? So now you can see, right, I've got my linear, oops, sorry. No, I did that backwards. This one's 3, and this one's here. Yeah, so this is our inner, and this is our outer. Sorry, I was backwards. Inner, outer. Okay, because it has the greater distance to our axis of revolution. All right, so I'm going to go, where am I revolving? Minus this to get my actual value. So it's 7 minus whatever that function is. 7 minus whatever that function is. And I'm going to get, watch your math, right? This is going to give you, okay, your radius, which I have to square. So pi r squared minus pi r squared. So pi outer squared minus pi inner squared. And I'm going to go from my bounds of integration, -2 to 1. Okay. Does anybody have other questions? You're welcome. You guys, if you want, please feel free to please come to class on Wednesday with a lot of questions like homework, quizzes, old exams, things like that. I don't want to talk about old exams now because those are more time consuming. And then we'll, because we only have a few minutes left. Nobody has any questions? Oh, can I ask about the concepts and lecture examples from 3.9? Sure. Let me get out my lecture examples for 3.9. Sure, what's up?
Yeah, so if I understand right, the work is supposed to be the integral of weight density times volume. Is that what we're essentially finding?
Yeah, so it's like if we're doing the work on some kind of a solid, right, or some kind of a so when we did our examples like 3 and I think 4, these are like some kind of liquid, right? So the liquid had like a weight density, right? So we needed to bring this. So this is the density is in basically a weight unit per cubic, feet or inches or whatever our metric was in, right? And then to get rid of this per cubic feet, I had to multiply by the volume, right? And so the volume is really just that. It's not the volume of the whole sphere. It's the volume of that tiny little cross-sectional circle that we're doing. But this volume here helps us set up our integral, right? Because this volume is that little sliver that we're going to be moving up out of the tank, right? So I've got this pi r, in this case, it's a sphere. So it's pi r squared is my cross-sectional area. And the thickness is just like the delta height, whatever, it's infinitely thin, right? That becomes our dy or our dh, if you want to think about it in terms of height, right? So that's this here, that volume. So then 50 pounds per cubic feet, this is going to be squared times feet. So we'll get like cubic feet right there.
Okay, that makes sense. Yeah, I originally thought that the volume was I thought the volume was referring to the volume of the entire like liquid rather than at an infinitesimally small like slab, I guess.
Yeah, and it has more to do with like the fact that we're it's not just that we have like a variable density. Like in this case, it isn't a variable density. It's like pretty consistent density throughout the whole thing. But the fact that like it's going to take less work to move this piece up because I'm only going 8 feet than if I were to take this piece and move it up 16 feet, right? So I have to be able to think about like the distance, right, that I'm traveling and that tiny little sliver. Like I'm going to take this little sliver and this little sliver and this little sliver. I'm not like, we did this as a back of the envelope calculation to see if we were on the right track. We took the whole tank and lifted it up, right? We said, what's the work required to lift this whole tank up? So pi r cubed is our volume of our whole, 4/3 pi r cubed is the volume of our whole sphere, right? It's half full and it has a weight density of, whatever our, our, liquid was, right? And so that kind of gives us, instead of saying, we had this variable force because the force of gravity to move from here or to here is going to be different, right? Because I've got this tank is half full, so I have to move these tiny little slivers and the force of gravity is going to be different depending on where I'm at, which is why we're thinking about it that way. It's a variable force. Okay, but we just wanted to compare it with if I took that, which is what you're thinking, right? That whole volume of the whole sphere and then lift it up. And that just gives us a ballpark measurement, right? But this is like a constant force essentially, right? Whereas this is much more accurate, right? Because I'm basically taking out all these tiny little slivers in cross-sectional area from my spherical tank, and I'm moving that top sliver 8 feet. I'm moving the next sliver down 8 feet and 1 nanometer, out, right? I mean, it's like I have to be able to take into account that variability as I go.
Okay, that makes a lot more sense. Yeah, the dy, so the dy is referencing the infinitesimally small volumes of the cross-sectional areas.
Right.
And the height is just referring to how far the variable distance that would have to be carried through to perform work.
Right, and that's that's going to depend on where you are in the tank, where the height of that little sliver is. And then the problem it becomes that we have this in terms of our radius, and this is in terms of y, and our distance is in terms of y. So I need to convert my radius to be in terms of y, so I have all the same variable that I'm working with, which is why we started talking about the equation of the circle, because the circle describes that sliver, that tiny little sliver, right? And I can solve it in terms of my radius, right? I'm sorry, I can solve it in terms of my x here. And I got lucky because I'm, you know, my x, the center point of my x is at 0. I mean, otherwise I would have to like, you know, FOIL these things out and then, you know, try to solve for x in a more reasonable way. But here it was just straightforward. I mean, I set the origin point so that it was right there, right?
Yeah.
So I could do that. And then this x allows me to write my radius in terms of y, because my radius is going to change depending on where I'm at, right? So my radius here is the biggest, but my radius down here is tiny, right? So my radius is really a function of y.
Okay, that makes sense. Thank you.
Yeah, which is what we're trying to do here. And the next problem, our radius is still a function of y, but we've got different geometry that we're dealing with.
Yeah, the relationship between x and y. I see.
Yeah.
Okay.
Yeah. It's hard to get your mind wrapped around. It does help. And I need to scan these in. I realize that. So you guys can have them. But there's a lot to kind of take into account. But we're talking about variable force, you know, which is why, you know, it's more complicated, why we have to integrate it. Okay, guys. I have office hours on Wednesday. If you guys want to come and ask more questions, you can come to class on Wednesday with lots of questions, hopefully, and we'll just do a review period. Okay, guys?
Thank you.
All right, you guys have a great day. I'll see you on Wednesday.
Thank you.
Bye.